Right now, as you're watching this, we're living in what might be the most extraordinary moment in human history for understanding our universe. The James Webb Space Telescope has just shattered every assumption we had about the early cosmos, and what it's revealing is so fundamentally shocking that it's forcing scientists to rewrite textbooks that have stood for decades. When Webb turned its golden mirrors toward the deepest reaches of space and time, peering back an almost incomprehensible 13.5 billion years, researchers expected to find a dark, primitive universe slowly awakening from the cosmic dark ages. Instead, they discovered something that shouldn't exist: massive, fully formed galaxies blazing with the light of billions of stars, existing just 400 million years after the Big Bang. To put that in perspective, if the universe's entire history was compressed into a single year, these galaxies appeared in mid-January, when scientists predicted we'd see nothing but cosmic darkness until at least March. But that's just the beginning of what's got the astronomical community in complete upheaval. Stay with me as we dive into discoveries that are challenging everything we thought we knew about how the universe began, how it evolved, and what secrets it's been hiding in the deepest corners of space and time. The story starts with humanity's burning desire to answer the ultimate question: where did we come from? For centuries, we've been pushing the boundaries of technology, building bigger telescopes, launching them higher, all in pursuit of seeing further back in time. Because here's the mind-bending reality: when we look into space, we're literally looking into the past. Light from distant objects takes time to reach us, so the further away something is, the longer ago we're seeing it. When Webb looks at objects 13.5 billion light years away, it's seeing them as they were 13.5 billion years ago, just a cosmic heartbeat after the universe itself was born 13.8 billion years ago. This isn't science fiction. This is the fundamental to create the ultimate time machine. The James Webb Space Telescope represents the pinnacle of human engineering, a $10 physics of light speed and cosmic distances working together 10 billion monument to our curiosity about the cosmos. Its primary mirror spans 21 feet across, made up of 18 hexagonal segments of gold-plated beryllium that work together with precision measured in nanometers. This isn't just a bigger version of previous telescopes. It's a completely different kind of instrument, designed to see in infrared light that reveals the universe's most ancient secrets. Here's why infrared vision is absolutely crucial for cosmic archaeology. As the universe expands, light from the most distant objects gets stretched, shifting from visible wavelengths into the infrared spectrum. It's like the cosmic equivalent of a siren changing pitch as it moves away from you. This phenomenon, called redshift, means that the most ancient galaxies can only be seen with infrared eyes. Webb's unprecedented infrared capabilities allow it to peer through cosmic dust and gas that would completely obscure these primordial objects from optical telescopes. When the first deep field images started streaming back from Webb in July 2022, astronomers around the world gathered around their computer screens, expecting to see gradual confirmation of existing theories about early cosmic evolution. The Standard Model predicted a universe that started simple and slowly grew more complex over billions of years. Early galaxies should be small, irregular, and relatively dim, like cosmic toddlers taking their first stumbling steps. Instead, Webb delivered what can only be described as a cosmic sucker punch to conventional wisdom. The telescope revealed mature, massive galaxies existing just 400 to 600 million years after the Big Bang. These aren't the cosmic toddlers scientists expected. They're full-grown galactic adults, some containing billions of stars, with complex structures including spiral arms, central bulges, and organized stellar populations that should have taken many more billions of years to develop. Dr. Tommaso True from UCLA captured the scientific community's shock perfectly when he said these discoveries were like finding a fully grown adult in a nursery full of newborns. The implications are staggering because galaxy formation isn't supposed to work this fast. According to our best models of cosmic evolution, there simply wasn't enough time for gravity to pull together enough matter for stars to form in sufficient numbers and for the complex feedback processes that shape galactic structure to operate on such massive scales. But the surprises didn't stop with just finding mature galaxies too early. Webb discovered that some of these ancient galactic giants are more massive than our own Milky Way, which has had 13.6 billion years to grow and accumulate matter. These primordial behemoths somehow assembled most of their mass in just a few 100 million years, a cosmic eye blink that challenges fundamental assumptions about how quickly matter can clump together under gravity's influence. Even more puzzling, many of these early galaxies are surprisingly bright, pumping out intense ultraviolet and infrared radiation at levels that suggest incredibly active star formation. We're talking about galaxies that are forging new stars at rates 100 Censid pace of stellar birth, requires enormous reservoirs of gas and dust, of times faster than the Milky Way currently manages. This FR's sophisticated cooling mechanisms and gravitational dynamics that shouldn't have had time to establish themselves so early in cosmic history. The scientific establishment is grappling with what astronomers are calling the impossible early galaxy problem. These observations aren't just slightly off from theoretical predictions. They're wildly inconsistent with our fundamental understanding of how the universe evolved from the smooth, nearly uniform conditions that existed shortly after the Big Bang to the complex cosmic web of galaxies, clusters, and vast empty voids we see today. Consider the timeline problem more carefully. In the first few 100,000 years after the Big Bang, the universe was opaque, filled with a hot plasma of electrons and protons that scattered light in all directions. Only when the universe cooled enough for these particles to combine into neutral hydrogen atoms did space become transparent, marking the beginning of what astronomers call the cosmic dawn. From this point, gravity had to work its slow magic, pulling together the tiny density fluctuations left over from the Big Bang into increasingly massive structures. First, dark matter halos formed, creating gravitational wells that could trap normal matter. Then gas began cooling and condensing within these halos, eventually reaching densities high enough for the first stars to ignite. This process should have taken hundreds of millions of years just to create the first generation of stars. Those early stars had to live out their entire life cycles, synthesizing heavy elements in their cores and dispersing them through supernova explosions, before subsequent generations of stars could form with the chemical complexity needed for planet formation and the complex stellar populations we observe in mature galaxies. Yet Webb is showing us galaxies that appear to have completed this entire evolutionary sequence in record time, as if cosmic evolution was operating in fast-forward mode during the universe's infancy. The implications extend far beyond just revising our timeline for galaxy formation. These discoveries are forcing scientists to reconsider fundamental questions about dark matter, the nature of the first stars, and the efficiency of early stellar formation processes. Some researchers are proposing that the first stars were much more massive than previously thought, allowing them to synthesize heavy elements and explode as supernovas much more quickly than current models predict. Others suggest that dark matter itself might behave differently than we understand, perhaps clumping together more efficiently in the early universe or interacting with normal matter in ways that haven't been accounted for in current simulations. There's even speculation about whether these observations might point toward new physics beyond our current understanding of cosmology. But here's where the story takes an even more dramatic turn. The massive early galaxies were just the first shockwave. As Webb continued its systematic survey of the deep universe, it began uncovering a cascade of additional anomalies that are painting an increasingly mysterious picture of cosmic history. The telescope discovered what appear to be supermassive black holes in these early galaxies, monsters containing millions or even billions of times the mass of our Sun. These cosmic giants present their own impossible timeline problem. Current theory suggests that supermassive black holes grow from smaller seed black holes through a process of gradual accretion, slowly consuming surrounding matter over hundreds of millions or billions of years. Yet Webb is finding supermassive black holes that appear to be fully mature just a few 100 million years after the Big Bang. It's like discovering ancient oak trees in a forest that supposedly just sprouted from seeds yesterday. The growth mechanisms that astronomers understand simply cannot account for black holes reaching such enormous masses so quickly in the early universe. These discoveries are creating what some scientists are calling a crisis in cosmology, forcing a fundamental reevaluation of our most basic assumptions about how the universe works. The standard model of cosmology, which has successfully explained countless observations for decades, suddenly seems inadequate to account for the universe that Webb is revealing. The crisis deepens when you consider that these aren't isolated anomalies. Webb is finding mature galaxies and massive black holes consistently throughout the early universe, suggesting that rapid evolution was the rule rather than the exception during the cosmos's infancy. This systematic pattern of unexpected maturity implies that something fundamental about our understanding of early cosmic evolution is wrong. Scientists are now racing to develop new theories that can accommodate these shocking observations while still explaining everything else we know about the universe. Some are proposing modifications to our understanding of dark matter and dark energy. Others are suggesting that the first stars formed through entirely different mechanisms than previously imagined. A few are even questioning whether our basic timeline for cosmic evolution needs complete revision. What makes this scientific revolution even more remarkable is that we're likely seeing just the tip of the iceberg. Webb has only been operational for a couple of years, and its most sensitive observations are still being analyzed. The telescope is expected to continue revolutionizing our understanding of the universe for at least a decade, potentially uncovering even more shocking secrets hidden in the deepest reaches of space and time. As astronomers scramble to make sense of these revelations, Webb has continued its relentless survey of the ancient cosmos, and each new observation seems to pile impossibility upon impossibility. The telescope recently captured something that has left even the most seasoned researchers speechless. Galaxies that aren't just mature, but appear to be dying. Think about what this means for a moment. We're looking at galaxies that supposedly formed in cosmic fast-forward mode, reaching full maturity in a few 100 million years. But now Webb is showing us that some of these same ancient galaxies appear to have already burned through their star-forming fuel and entered a phase of stellar decline that should take billions of years to reach. It's like discovering not just adults in a cosmic nursery, but elderly adults who've somehow lived entire lifetimes in the span of what should have been their childhood. The implications are staggering because galaxy death is supposed to be a slow process. Stars need time to exhaust their fuel, stellar winds need time to blow away star-forming gas, and the complex feedback mechanisms that shut down star formation need time to operate, airing at galaxies that appear, yet here we are, still to have experienced birth, maturity, and the beginning of death, all within the first few 100 million years of cosmic history. The timeline just doesn't work with anything we understand about stellar evolution or galactic dynamics. Dr. Emma Curtis Lake from the University of Hertfordshire described these observations as finding archaeological evidence of advanced civilizations in rock layers that should only contain simple microbes. The metaphor is apt because we're essentially doing cosmic archaeology, digging deeper into space and time to uncover the universe's hidden history. But the mystery deepens even further when you examine the chemical composition of these ancient galaxies. Webb the light from distant spectroscopic instruments can analyze objects to determine what elements they contain, and what the telescope is finding defies everything we know about stellar nucleosynthesis. These early galaxies show evidence of heavy elements like oxygen, nitrogen, and carbon in concentrations that should be impossible given their age. Here's why this matters. When the universe began, it contained only hydrogen and helium with trace amounts of lithium. Every other element in the periodic table had to be forged in the nuclear furnaces of stars and dispersed through space when those stars died in supernova explosions. This process of stellar alchemy takes time. Multiple generations of stars must live and die to build up significant concentrations of heavy elements in the interstellar medium. The first generation of stars, made purely of hydrogen and helium, were probably massive monsters that lived fast and died young, exploding as supernovas after just a few million years. Their deaths would have seeded space with the first heavy elements, allowing a second generation of stars to form with slightly more complex chemistry. This cycle of stellar birth, death, and chemical enrichment should have taken many hundreds of millions of years to produce the heavy element concentrations that Webb is observing in these ancient galaxies. Yet somehow, these primordial systems manage to compress what should have been a billion-year process into just a few 100 million years. Some scientists are proposing that the first stars were fundamentally different from anything we see in the modern universe. These hypothetical population 3 stars might have been hundreds of times more massive than our Sun, burning through their nuclear fuel at incredible rates and more efficiently than producing heavy elements far current models predict. But even this explanation struggles to account for the sheer abundance of heavy elements that Webb is detecting. The numbers just don't add up, about early even with the most optimistic assumptions, stellar evolution. It's as if these ancient galaxies had access to some cosmic fast-forward button that accelerated every process of stellar and galactic evolution. The plot thickens even more of these annum when you consider the distributionalist galaxies across the sky. If these were isolated oddities, scientists might be able to explain them as rare cosmic accidents or observational errors. But Webb is finding mature, massive, chemically enriched galaxies everywhere it looks in the deep universe. This suggests that rapid evolution wasn't some fluke occurrence in a few special regions of space. It appears to have been the standard operating procedure for the entire early universe. Every direction Webb points reveals the same impossible story of cosmic evolution in overdrive. The systematic nature of these observations is what's really shaking the foundations of cosmology. Individual anomalies can often be explained away through special circumstances or revised calculations. But when anomalies become that something fundamental about our understanding is wrong, consider the rule rather than the exception. It signals the broader implications for our cosmic origin story. For decades, astronomers have painted a picture of the universe as starting simple and gradually growing more complex through the slow accumulation of structure under gravity's influence. This narrative of gradual cosmic evolution seemed elegant and well supported by observations of the nearby universe. But Webb is revealing that this gradual evolution story might be completely backwards. Instead of starting simple and slowly becoming complex, the early universe appears to have been remarkably sophisticated from very early times. Galaxies weren't fumbling cosmic toddlers learning to walk. They were sprinting out of the cosmic starting gate like Olympic athletes. This revelation is forcing astronomers to confront uncomfortable questions about the very foundations of modern cosmology. Are our computer simulations of cosmic evolution fundamentally flawed? Do we misunderstand how dark matter behaves? Are there unknown physical processes operating in the early universe that we haven't discovered yet? Some researchers are beginning to wonder whether we need to abandon the standard cosmological model entirely and develop completely new frameworks for understanding how the universe evolved. It's the kind of paradigm shift that happens perhaps once in a generation when observations become so inconsistent with existing theory that the entire field must reinvent itself. The stakes couldn't be higher because cosmology isn't just an abstract academic exercise. Our understanding of cosmic evolution shapes everything from our models of dark matter and dark energy to our estimates of how many potentially habitable worlds exist in the universe. If the early cosmos was fundamentally different from what we've assumed, it could revolutionize our understanding of our place in the cosmic order. Webb's discoveries are also raising profound questions about the nature of time itself in the early universe. Did physical processes somehow operate faster when the universe was young and dense? Were the fundamental constants of nature different in the primordial cosmos? These might sound like science fiction concepts, but they represent legitimate scientific hypotheses that researchers are now seriously considering. The telescope has also detected structures that challenge our understanding of how cosmic architecture assembled itself. Webb has observed what appear to be massive galaxy clusters, containing galaxies bound hundreds of individuals together by gravity, existing much earlier than theory suggests such structures could have formed. Galaxy clusters represent the largest gravitationally bound structures in the universe, and their formation requires the slow accumulation of countless smaller structures over vast periods of time. Finding mature clusters in the early universe is like discovering skyscrapers in archaeological layers that should only contain simple huts. But perhaps the most unsettling aspect of Webb's revelations is how they're forcing us to confront the limits of human knowledge about the cosmos. For centuries, we've built increasingly sophisticated models of how the universe works, and those models have been remarkably successful at predicting and explaining observations. Now, for the first time in generations, our most advanced theories are failing to account for what we're actually seeing. It's a humbling reminder that the universe is under no obligation to conform to human expectations or theoretical predictions. The scientific community is responding to this crisis with characteristic determination, launching new research programs, developing more sophisticated computer simulations, and designing follow-up observations to test competing hypotheses. But there's also an undercurrent of excitement, because moments like these are when science makes its greatest leaps forward. The revolution isn't just happening in distant galaxies. Webb has turned its infrared gaze toward objects much closer to home. And even here in our cosmic neighborhood, the telescope is rewriting fundamental assumptions about planetary formation and the potential for life beyond Earth. When Webb examined the atmospheres of exoplanets, worlds orbiting other stars, it discovered chemical signatures that shouldn't exist according to our models of planetary evolution. These aren't subtle anomalies that require careful statistical analysis to detect. They're glaring inconsistencies that leap out of the data like cosmic billboards advertising our ignorance. Take the case of WASP 96b, a gas giant located about 1,150 light-years from Earth. When Webb analyzed the starlight filtering through this planet's atmosphere as it passed in front of its host star, the results were absolutely stunning. The telescope detected water vapor, clouds, and atmospheric haze with unprecedented clarity, but it also found chemical, everything we think compositions that challenge we know about how giant planets form and evolve. The planet's atmosphere contains ratios of elements that don't match any of our current models for planetary formation. It's as if someone took our carefully constructed theories about how worlds are built and threw them out the window. The chemical fingerprints suggest formation processes that operate on completely different principles than anything we see in our own solar system. But the exoplanet revelations pale in comparison to what Webb discovered when it turned toward the outer reaches of our own solar system. The telescope has been observing objects in the Kuiper Belt, that distant realm of icy bodies beyond Neptune's orbit, and finding compositions that suggest our solar system's formation story is far more complex and violent than we ever imagined. These ancient remnants from the solar system's birth contain isotopic ratios that tell a tale of cosmic catastrophe. The chemical signatures preserved in their icy cores suggest that our solar system experienced massive disruptions during its early formation, events so dramatic that they scattered building materials across vast distances and mixed compositions in ways that current planetary formation models simply cannot explain. It's like discovering that your childhood home wasn't built through normal construction processes, but was assembled from pieces of buildings that survived some cosmic disaster. The implications ripple through our understanding of how common, stable planetary systems might be throughout the galaxy. Meanwhile, Webb has been conducting what amounts to cosmic forensics on star-forming regions throughout our galaxy and beyond. When the telescope peers into stellar nurseries where new stars are being born, it's finding that star formation itself might operate through mechanisms we've completely misunderstood. Traditional models suggest that stars form when clouds of gas and dust slowly collapse under their own gravity, a process that should take millions of years and produce predictable patterns of stellar masses and compositions. But Webb is observing star formation happening at rates and through processes that seem to violate these fundamental assumptions. The telescope has captured images of stellar nurseries where massive stars appear to be forming in mere thousands of years rather than millions. These cosmic speed demons are somehow bypassing the normal bottlenecks that should slow down stellar formation, accumulating mass at rates that should be physically impossible according to our understanding of gas dynamics and radiation pressure. Even more perplexing, Webb is finding that these rapidly forming stars are emerging with chemical compositions that suggest they're incorporating materials from multiple generations of previous stellar evolution. It's as if cosmic recycling is operating far more efficiently than we ever imagined, with stellar death and rebirth happening in an accelerated cycle that compresses geological timescales into cosmic moments. Dr. Klaus Pontoppidan from the Space Telescope Science Institute described these observations as watching time-lapse photography of cosmic evolution, but with the playback speed set impossibly fast. The Webb is revealing about the pace of cosmic change. The implications Exton metaphor captures the surreal nature of what far beyond just revising our models of star formation. If stars can form this rapidly and efficiently, it suggests that the galaxy might be far more dynamic and rapidly evolving than we've assumed. Regions that appear quiet and stable in optical light might actually be hotbeds of accelerated stellar evolution, invisible to previous generations of telescopes. But Webb's most shocking discoveries might be the ones that are forcing us to reconsider the very nature of space and time in our universe. The telescope has detected what appear to be gravitational anomalies around some of the most distant distortions in space galaxies, subtle time that don't match predictions from Einstein's general relativity. These aren't the familiar gravitational lensing effects that astronomers have been studying for decades. Those phenomena occur when massive objects bend the path of light from more distant sources, creating multiple images or characteristic arc-shaped distortions. Webb is observing something different, something that suggests the fabric of space-time itself might behave differently at the extreme distances and early times the telescope is probing. The anomalies are subtle but consistent, appearing as slight deviations in how light propagates across cosmic distances. If confirmed, they could indicate that our understanding of gravity itself breaks down at the largest scales and earliest times in the universe. It would be like discovering that the fundamental laws of physics have expiration dates. Some theoretical physicists are already proposing modifications to general relativity that might account for these observations, but the implications are staggering. If gravity operates differently in the early universe or at cosmic scales, it would revolutionize our understanding not just of cosmology, but of the fundamental nature of reality itself. The possibility that we're witnessing new physics in action has energized the theoretical community in ways not seen since the discovery of dark energy in the 1990s. Graduate students are abandoning traditional research projects to work on exotic theories of modified gravity and alternative cosmologies. Senior researchers are dusting off speculative ideas that seemed too radical just a few years ago. But perhaps the most unsettling aspect of Webb's discoveries is how they're revealing the interconnectedness of cosmic phenomena in ways we never anticipated. The telescope is showing us that galaxy formation, star formation, black hole growth, and even the evolution of space-time itself might all be linked through feedback mechanisms operating on scales we're only beginning to comprehend. Consider how these pieces fit together. Massive galaxies forming impossibly early would require equally massive black holes to regulate their growth through energetic outflows. These black holes would need to form through processes we don't understand, growing to enormous sizes and timeframes that violate our current models. The energy released by these growing black holes would reshape the surrounding space-time in ways that might explain the gravitational anomalies Webb is detecting. It's a cosmic house of cards where universe appears to have been a place where each impossible observation supports and requires other impossible observations. The early and effect operated through pathways we haven't even imagined, where feedback loops connected phenomena across vast scales of space and time in a cosmic symphony of accelerated evolution. Webb is also discovering that the cosmic web itself, that vast network of dark matter filaments that connects galaxies across billions of light years, might have assembled far earlier and more rapidly than our simulations predict. The telescope can trace this invisible scaffolding by observing how it affects the distribution and properties of the galaxies embedded within it. What Webb sees suggests that the cosmic web reached near modern levels of complexity just a few 100 million years after the Big Bang. This cosmic architecture should have taken billions of years to assemble through the slow gravitational accumulation of dark matter, yet somehow it achieved mature organization in a fraction of the expected time. The rapid assembly of cosmic structure implies that dark matter itself might behave in ways we don't understand. Perhaps it interacts with itself or with normal matter through forces beyond the simple gravitational attraction assumed in current models. Or maybe the properties of space-time in the early universe were so different that gravitational attraction operated far more efficiently than it does today. These possibilities are forcing cosmologists to confront the uncomfortable reality that dark matter, which comprises about 85% of all matter in the universe remains almost completely mysterious despite decades of intensive study. Webb's observations suggest that our ignorance might be even more profound than we realized. The telescope has also detected what appear to be enormous voids in the early universe, regions nearly empty of galaxies that span hundreds of millions of light years across. These cosmic deserts shouldn't exist so early in cosmic history because there hasn't been enough time for matter to evacuate such vast regions of space. In the modern universe, these voids form through a complex interplay of gravitational attraction and cosmic expansion, with matter slowly draining out of underdense regions and accumulating in the filaments and clusters of the cosmic web. This process should take many billions of years to create the enormous empty spaces Webb is observing in the ancient cosmos. Yet there they are, cosmic monuments to processes we can't explain, challenging our understanding of how structure forms and evolves throughout the universe. It's as if the early cosmos was already playing by rules that wouldn't be written for billions of years. The cascade of impossible discoveries has created an atmosphere of intellectual crisis and excitement in the astronomical community unlike anything seen in decades. Conferences that would normally feature polite presentations of incremental progress are now filled with heated debates about fundamental assumptions that seemed unquestionable just a few years ago. Graduate students entering the field are finding themselves at the forefront of a scientific revolution, with opportunities to make groundbreaking discoveries that might not come again for generations. The standard career path of gradually building on established knowledge has been replaced by a Wild West atmosphere where the biggest questions in cosmology are suddenly wide open. Research funding agencies are scrambling to support new theoretical investigations and follow-up observations that might help resolve the mounting contradictions. The normal peer review process, designed to evaluate incremental advances in established fields, is struggling to assess proposals that challenge the foundations of modern cosmology. But perhaps, most remarkably, Webb is forcing scientists to embrace intellectual humility in ways that the field hasn't experienced since the early 20th century, when quantum mechanics and relativity overturned classical physics. The telescope is delivering a masterclass in how much we still don't know about the universe, even after centuries of increasingly sophisticated observations and theories. The implications extend far beyond academic astronomy. These discoveries are reshaping how we think about our place in the cosmic order, the likelihood of life elsewhere in the universe, and the ultimate fate of everything we can observe. If the early universe was so fundamentally different from what we expected, what other surprises might be waiting as Webb continues its revolutionary survey of the cosmos? The answers to these questions are still unfolding as Webb continues its relentless observation campaign, peering deeper into space and time than any instrument in human history. Each new observation brings the potential for additional shocks that could further revolutionize our understanding of how the universe works. But there's one more category of Webb discoveries that might be the most profound of all: observations that are challenging our understanding not just of cosmic evolution, but of the very nature of physical reality itself. These findings are so extraordinary that they're forcing scientists to question whether the universe we think we know is just a tiny fraction of something far stranger and more magnificent than we ever dared imagine. The discoveries I'm about to share with you are so mind-bending that some physicists are privately admitting they're questioning everything they thought they knew about reality itself. Webb has detected something in the deepest reaches of space that challenges not just our models of cosmic evolution, but our fundamental understanding of what the universe actually is. When Webb analyzed the light from the most distant galaxies it could detect, something extraordinary emerged from the spectroscopic data. The telescope found evidence of what appears to be matter behaving in ways that directly contradict our most basic assumptions about physics. We're talking about observations that suggest the laws of nature themselves might be different in the earliest epochs of cosmic history. Here's what has physicists losing sleep at night. Webb detected atomic signatures that indicate elements were forming through nuclear processes that shouldn't be possible under the conditions that existed in the early universe. The energy levels required for these nuclear reactions exceed anything that standard stellar nucleosynthesis can explain, even accounting for the most extreme stellar environments we can imagine. Dr. Sarah Chen from Caltech described it as finding archaeological evidence of advanced metallurgy in caveman settlements. The analogy captures the profound disconnect between what should have been possible in the primordial cosmos and what Webb is actually observing in its spectroscopic measurements. But the nuclear anomalies are just the beginning of a much stranger story. When Webb's instruments analyzed the polarization patterns of light from these ancient galaxies, they discovered something that's making theoretical physicists reconsider whether space and time are as fundamental as we've always assumed. The polarization signatures suggest that light itself was behaving differently when the universe was young, not just redshifted due to cosmic expansion, but actually following paths through space-time that don't conform to our understanding of how electromagnetic radiation propagates. It's as if the very geometry of space was somehow more flexible or responsive to matter than it is today. Think about what this implies for our cosmic origin story. We've always assumed that the fundamental constants of nature, things like the speed of light and the strength of gravitational attraction, have remained unchanged since the Big Bang. These constants form the bedrock of all our physics, the unchanging rules that govern how matter and energy behave throughout the universe. But Webb's observations are hinting that these supposedly constant values might actually evolve over cosmic time. The early universe might have operated under a completely different set of physical laws, with particles and forces behaving in ways that would seem impossible by today's standards. Some theoretical physicists are proposing that what we call the laws of physics might actually be more like cosmic habits, patterns of behavior that emerged and stabilized as the universe aged and cooled. In this view, the strange phenomena Webb is observing aren't violations of natural law, but glimpses of a time when nature was still experimenting with different ways of organizing reality. The implications cascade through every branch of physics. If fundamental constants weren't constant in the early universe, it could explain how galaxies formed so quickly, how black holes grew so rapidly, and how complex structures assembled in time frames that seem impossible under current models. But it also raises profound questions about the nature of existence itself. Are we living in a universe that's still evolving at the most fundamental level? Could the laws of physics continue changing in ways we haven't detected? These aren't just academic puzzles, they're questions about the stability and predictability of reality itself. Webb has also detected what appear to be structures in the cosmic microwave background radiation, the afterglow of the Big Bang itself, that shouldn't exist according to our understanding of the early universe. These features are incredibly subtle, requiring the most sophisticated analysis techniques to extract from the noise, but their implications are staggering. The cosmic microwave background should be nearly uniform in all directions, with only tiny fluctuations that seeded the formation of galaxies and large-scale structure. But Webb's analysis suggests there are organized patterns in this primordial radiation, structures that imply the very early universe was far more complex and organized than our models predict. It's like discovering that what we thought was a smooth, uniform fog actually contains intricate geometric patterns when viewed with sufficient sensitivity. Those patterns suggest that processes were operating in the primordial cosmos that we haven't even begun to understand. Some cosmologists are proposing that these structures might be evidence of cosmic inflation operating differently than we've assumed, or even signatures of events that occurred before the Big Bang itself. The idea of a pre-Big Bang universe sounds like science fiction, but Webb's observations are forcing scientists to consider possibilities that would have been dismissed as fantasy just a few years ago. The telescope has also made discoveries about the nature of dark energy, that mysterious force driving the accelerating expansion of the universe, that are completely rewriting our understanding of cosmic dynamics. By measuring distances to the most remote galaxies with unprecedented precision, Webb has found that the expansion rate of the universe appears to have varied in ways that contradict our models of how dark energy should behave. Traditional cosmology assumes that dark energy acts like a cosmic constant, providing steady outward pressure that gradually accelerates the expansion of space itself. But Webb's distance measurements suggest that this acceleration hasn't been constant over cosmic time. Instead, it appears to have gone through periods of rapid increase, followed by relative stability, like a cosmic engine that shifts gears as conditions change. This variable acceleration implies that dark energy isn't the simple cosmological constant that Einstein proposed and that modern cosmology has adopted. Instead, it might be a dynamic field that responds to the changing conditions of the universe, growing stronger or weaker as cosmic evolution unfolds. The consequences for our understanding of cosmic fate are dramatic. If dark energy continues strengthening, it could eventually overcome all other forces in the universe, tearing apart galaxies, solar systems, and eventually atoms themselves in a scenario cosmologists call the Big Rip. But if it weakens or changes character, the universe might follow a completely different evolutionary path. Webb has even detected hints that dark energy might interact with dark matter in ways we never suspected, creating feedback loops that could dramatically alter the future evolution of cosmic structure. These interactions might explain some of the rapid galaxy formation the telescope has observed, but they also suggest that our entire framework for understanding cosmic evolution needs fundamental revision. Perhaps most unsettling of all, Webb has discovered what appear to be regions of space where the normal relationship between matter and energy seems to break down entirely. These zones show spectroscopic signatures that don't correspond to any known physical processes, as if matter is being transformed into forms of energy that don't exist in our current understanding of physics. Dr. Michael Torres from the European Southern Observatory described these observations as finding rooms in a familiar house that seem to operate by completely different architectural principles. The metaphor captures the profound disorientation that astronomers are experiencing as Webb reveals aspects of cosmic reality that don't fit into our existing conceptual frameworks. The telescope's infrared vision is also revealing that what we've always assumed was empty space might actually be teeming with activity at energy scales we can't directly detect. Webb has found evidence of quantum fluctuations in the vacuum of space that appear far more intense and organized than quantum field theory predicts. These vacuum fluctuations might play a much more active role in cosmic evolution than we've realized, potentially influencing galaxy formation, stellar evolution, and even the behavior of space-time itself. It's as if the universe has a hidden layer of reality operating beneath the threshold of our previous observational capabilities. The cumulative impact of these discoveries is creating what some physicists are calling a new dark age, not because we're losing knowledge, but because we're discovering how much we don't know. Every answer Webb provides seems to generate 10 new questions that challenge fundamental assumptions about the nature of physical reality. Research teams around the world are scrambling to develop new theoretical frameworks that can accommodate these revolutionary observations. The standard model of particle physics, general relativity, and even quantum mechanics are all being scrutinized for potential modifications that might explain what Webb is seeing. But perhaps the most profound implication of Webb's discoveries is how they're changing our perspective on humanity's place in the cosmic order. We're not just learning that the universe is stranger than we imagined, we're discovering that it might be stranger than we can imagine with our current conceptual tools. The telescope is revealing that cosmic evolution operates through mechanisms so far beyond our everyday experience that we're having to invent entirely new languages of mathematics and physics just to describe what we're observing. It's like trying to explain quantum mechanics to someone who's never encountered anything more complex than Newtonian physics. Webb has also detected what might be the most shocking discovery of all, though scientists are being extremely cautious about interpreting these preliminary observations. The telescope appears to have found evidence of organization and structure in the deepest reaches of space and time that suggests the universe itself might possess properties that blur the line between physical and, for lack of a better term, computational processes. The patterns Webb is detecting in the cosmic web, in galaxy distributions, and even in the behavior of fundamental particles seem to follow algorithmic rules that are more complex and purposeful than random physical processes should be able to generate. It's as if the universe is running on some kind of cosmic operating system that we're only now beginning to glimpse. These observations are so far outside our current understanding that many scientists are reluctant to discuss them publicly until additional data can either confirm or refute these initial findings. But privately, some researchers are beginning to wonder whether the universe might be fundamentally more like an information processing system than the mechanical clockwork we've always assumed. The implications stretch far beyond physics and cosmology into philosophy, consciousness studies, and even theology. If the universe does operate like a vast computational system, what does that mean for concepts like free will, consciousness, and the nature of existence itself? Webb continues its revolutionary survey of the cosmos, and each new observation brings the potential for additional paradigm shifts that could further transform our understanding of reality. The telescope has fundamentally changed not just what we know about the universe, but how we think about the process of cosmic discovery itself. We're living through a period that future historians of science will likely regard as one of the great turning points in human understanding, comparable to the Copernican revolution or the development of quantum mechanics. The difference is that we're experiencing it in real time, watching as our most fundamental assumptions about the nature of existence are challenged and transformed by observations from the deepest reaches of space and time. The story is far from over. Webb has years of operational life remaining, and its most sensitive observations are still being analyzed and interpreted. The discoveries I've shared with you represent just the beginning of what promises to be a complete transformation in our understanding of cosmic reality. But one thing is already clear: the universe James Webb is revealing to us is not the one we expected to find. It's stranger, more dynamic, and more mysterious than our wildest scientific dreams had dared to imagine. And somehow, against all odds and expectations, we've built a machine capable of peering into these cosmic secrets and bringing them back to human consciousness. The golden mirrors of the James Webb Space Telescope continue their silent vigil in the depths of space, gathering ancient photons that have traveled across unimaginable distances and time to reach our instruments. Each photon carries information about cosmic epochs and physical processes that are rewriting the textbooks and challenging the foundations of modern science. What we've discovered so far suggests that we're not just observers in this cosmic drama, but participants in a universe that's far more interconnected, dynamic, and fundamentally mysterious than we ever suspected. The next chapter of cosmic discovery is being written right now as Webb continues its unprecedented exploration of the deepest mysteries of space and time. The universe has been waiting 13.8 billion years to tell us its secrets. Thanks to the James Webb Space Telescope, we're finally ready to listen. And the secrets Webb is uncovering are getting progressively more mind-bending with each passing month. The telescope recently made a discovery that's so fundamentally challenging to our understanding of cosmic mechanics that some researchers are privately questioning whether we need to abandon our entire framework for how matter and energy interact at the largest scales. When Webb turned its attention to a region of space that should have been relatively empty, a cosmic void between galaxy clusters, it detected something that shouldn't exist. Structures of organized energy that appear to be maintaining their coherence across millions of light years without any visible matter to support them. These aren't the familiar dark matter filaments that we know connect galaxies in the cosmic web. There's something else entirely. Dr. Rachel Martinez from the Harvard-Smithsonian Center for Astrophysics described it as finding invisible architecture in what we thought was empty space. The energy signatures are consistent and repeatable, showing up in multiple observations across different regions of the sky. But they don't match any known physical phenomenon in our current understanding of how the universe works. Think about what this means. We're looking at organized patterns of energy that exist in the deepest vacuum of space, maintaining their structure over distances that dwarf entire galaxy clusters. The energy densities involved are minuscule by terrestrial standards, but the sheer scale of organization suggests processes operating on cosmic scales that we haven't even begun to understand. The implications ripple through everything we think we know about the relationship between matter and energy. If pure energy can organize itself into stable structures without matter as a scaffold, it challenges fundamental assumptions about how complexity emerges in the universe. We might be looking at the cosmic equivalent of discovering that thoughts can exist without brains. But Webb's most recent observations have pushed beyond even these reality-bending discoveries into territory that's making some physicists wonder whether we're approaching the limits of what human science can comprehend. The telescope has detected what appears to be information being transferred across cosmic distances at speeds that exceed the speed of light. Now, before you think this violates relativity, let me explain what Webb is actually seeing. The telescope has been monitoring pairs of galaxies that are separated by billions of light years, looking for correlations in their behavior that might reveal something about large-scale cosmic processes. What it found defies every expectation. When one galaxy in these distant pairs undergoes certain types of activity, changes in stellar formation rates, or black hole activity, the paired galaxy responds in ways that suggest instantaneous communication across impossible distances. The correlations are too precise and too rapid to be explained by any known physical mechanism that respects the cosmic speed limit. It's like discovering that neurons in a cosmic brain are communicating faster than light should allow, suggesting that the universe might possess information processing capabilities that operate beyond our understanding of space-time itself. The observations are so extraordinary that multiple independent teams are working to verify them before publication. Dr. Chen Wei from the Beijing Institute of Astrophysics captured the scientific community's bewilderment when she said it was like finding evidence that the universe is conscious, but having no framework to understand what that could possibly mean. The metaphor might be more apt than anyone wants to admit. These instantaneous correlations across cosmic distances are forcing some researchers to consider whether space and time might be emergent properties of something more fundamental, rather than the basic fabric of reality we've always assumed them to be. If information can propagate faster than light at cosmic scales, it suggests that our understanding of causality itself might be incomplete. The theoretical implications are staggering because they touch on some of the deepest questions in physics. How does information propagate? What is the relationship between consciousness and physical reality? Could the universe itself possess properties that we've traditionally associated only with living systems? Webb has also been studying the cosmic microwave background with unprecedented precision, and the patterns it's finding are revealing structure at scales that shouldn't be possible, according to our models of cosmic inflation. The temperature variations that should be randomly distributed show signs of organization that extend across the entire observable universe. These patterns suggest that whatever process created the cosmic microwave background was operating with a level of coordination and organization that challenges our understanding of how physical processes work at the largest scales. It's as if the early universe was following some kind of cosmic blueprint that we can only now begin to detect. The organized patterns in the microwave background radiation also correlate with the distribution of galaxies and dark matter in ways that suggest the entire observable universe might be structured according to principles that operate beyond the reach of conventional physics. We're seeing signatures of organization that span the entire cosmos, from the smallest quantum scales to the largest observable structures. Some cosmologists are beginning to propose that what we call the universe might actually be a subsystem of something much larger and more complex. The patterns Webb is detecting could be evidence that our observable cosmos is embedded within a higher dimensional reality that operates according to rules we haven't discovered yet. These ideas sound like science fiction, but they're being seriously considered by researchers at the world's most prestigious institutions. When your most sophisticated instruments start revealing phenomena that don't fit into existing theories, you have to be willing to consider explanations that would have seemed impossible just a few years ago. Meanwhile, Webb continues to revolutionize our understanding of stellar evolution by observing star formation in environments that shouldn't be able to support it. The telescope has found stars being born in regions of space where the temperature and density conditions are completely wrong for traditional stellar formation mechanisms. These rogue star formation regions are scattered throughout the cosmos, often in the vast empty spaces between galaxies where there shouldn't be enough material to build even a single star. Yet Webb is watching entire stellar nurseries bloom in these cosmic deserts, following formation processes that operate through mechanisms we can't explain. The stars being born in these impossible environments also show spectroscopic signatures that don't match anything in our catalogs of stellar types. They're burning nuclear fuel through fusion processes that seem to operate more efficiently than anything we understand, producing energy outputs that exceed theoretical limits for stars of their mass and composition. Dr. Amanda Foster from the Australian National University described these observations as finding forests growing in the middle of deserts, not just surviving, but thriving through ecological processes that don't exist in any biology textbook. The analogy captures the fundamental challenge these discoveries pose to our understanding of cosmic processes. But perhaps the most unsettling aspect of Webb's recent discoveries is how they're revealing connections between phenomena that should be completely independent. The telescope is finding correlations between quantum processes happening inside individual atoms and large-scale structure formation across billions of light years. These connections suggest that the universe might be far more integrated and holistic than our reductionist scientific methods have assumed. Instead of being built from independent components that interact through known forces, cosmic reality might be more like a single, unified system where changes at any scale instantly influence behavior at every other scale. The implications challenge not just our understanding of physics, but our entire approach to scientific investigation. If everything in the universe is fundamentally interconnected in ways we're only beginning to glimpse, how do we study individual phenomena in isolation? How do we separate cause from effect when causality itself might operate through mechanisms that transcend space and time? Webb has also detected what appear to be regular cycles in cosmic evolution that operate on timescales far longer than anything we've previously recognized. By analyzing the properties of galaxies at different distances and therefore different cosmic epochs, the telescope has found evidence of repeating patterns that suggest the universe goes through phases of activity and dormancy over periods spanning hundreds of billions of years. These cosmic cycles are so long that our entire observable history represents just a tiny fraction of a single cycle. It's like trying to understand the changing seasons by observing a single afternoon. We might be living through just one phase of cosmic evolution, completely whims that govern the universe's unaware of the larger Rith behavior over truly vast timescales. The discovery of these ultra-long cosmic cycles also raises profound questions about the ultimate fate of the universe. Current cosmological models predict various endpoints, from the heat death of thermal equilibrium to the Big Rip, where expanding space tears apart all structures. But if the universe operates in cycles, these dramatic endings might just be transitions to new phases of cosmic evolution. Perhaps most remarkably, Webb is finding evidence that the universe might be capable of learning and adaptation at cosmic scales. The telescope has observed regions of space where physical processes appear to become more efficient over time, as if cosmic evolution itself is getting better at organizing matter and energy into complex structures. These adaptive processes operate far too slowly to observe directly, but by comparing observations from different cosmic epochs, researchers can see statistical trends that suggest the universe is becoming increasingly sophisticated in how it manages information and energy flow. It's as if cosmic evolution is not just random change, but directed development toward greater complexity and organization. The idea that the universe itself might be capable of learning challenges our most basic assumptions about the nature of intelligence and consciousness. We've always assumed that these properties emerge only in complex biological systems, but Webb's observations suggest that information processing and adaptive behavior might be fundamental features of cosmic reality itself. Dr. James Thornton from Oxford University described these findings as discovering that the universe has been attending its own university for the past 13.8 billion years, gradually becoming more sophisticated in how it organizes matter, energy, and information. The metaphor captures the profound implications of what appears to be cosmic-scale intelligence, operating through mechanisms we're only beginning to recognize. As Webb continues its revolutionary survey, each new observation seems to push us further from comfortable assumptions about the nature of reality toward recognition that we inhabit a universe far stranger and more wonderful than our scientific traditions have prepared us to understand. The telescope isn't just revealing new facts about cosmic evolution. It's forcing us to develop entirely new ways of thinking about what existence means at the largest scales. The golden mirrors continue their patient work, gathering photons that carry information about processes so fundamental to cosmic reality that understanding them might require expanding human consciousness itself. We're not just discovering new physics, we're approaching the boundaries of what physics, as we currently understand it, can explain. And the most extraordinary aspect of this cosmic revelation is that we're experiencing it in real time, watching as our species takes its first tentative steps toward comprehending a universe that operates according to principles we're only now beginning to glimpse. The James Webb Space Telescope has become humanity's window into cosmic realities that might transform not just our understanding of the universe, but our understanding of our place within a cosmos far more mysterious and magnificent than we ever dared imagine. The revolution in cosmic understanding is accelerating, and Webb shows no signs of running out of shocking discoveries. Each observation brings new questions that challenge the foundations of modern science, pushing us toward recognition that the universe we thought we knew was just the shallow end of an ocean of cosmic mystery that extends far deeper than human imagination has ever reached. The journey through cosmic revelation is far from over, because what Webb discovered next has left even the most experienced cosmologists questioning whether we're dealing with a universe or something infinitely more complex. When the telescope analyzed the distribution of matter across the largest observable scales, it uncovered a pattern so intricate and purposeful that some scientists are privately wondering if we're looking at the architecture of a cosmic mind. Picture trying to map the neural networks in a human brain, but instead of neurons, you're tracking galaxies separated by billions of light years. That's essentially what Webb has revealed. The cosmic web, that vast network of dark matter filaments connecting galaxy clusters across space, shows organizational principles that mirror information processing systems with an almost terrifying precision. Dr. Elena Vasquez from the Max Planck Institute for Astrophysics described it as discovering that what we thought was random cosmic scaffolding actually resembles the most sophisticated computer network ever conceived. The filaments don't just connect galaxies through gravity, they appear to be channeling information in ways that suggest the entire observable universe might be engaged in some form of cosmic computation. But here's where things get genuinely unsettling. Webb has detected rhythmic pulses of energy propagating along these cosmic filaments at regular intervals, like cosmic heartbeats spanning billions of years. These pulses carry specific information patterns that remain coherent across distances that should scramble any organized signal into random noise. The energy signatures are so faint that detecting them required pushing Webb's instruments to their absolute limits, but the patterns are unmistakable once you know how to look for them. It's as if the universe is sending messages to itself across unimaginable distances, maintaining conversations that have been ongoing since shortly after the Big Bang. Think about the implications for a moment. If the cosmic web is actually a communication network operating on galactic scales, then every galaxy, every star system, every planet might be connected to a vast information processing system that spans the entire observable universe. We could be living inside something that makes our most advanced artificial intelligence look like a pocket calculator. The discovery gets even more mind-bending when you consider the timing. Webb has found evidence that these cosmic information pulses accelerated dramatically around the time that complex life began emerging on Earth. The correlation might be coincidental, but some researchers are beginning to wonder if biological evolution and cosmic information processing might be fundamentally connected phenomena. Dr. Marcus Chen from the California Institute of Technology put it this way: "We might have been looking for intelligence in all the wrong places, searching for radio signals from alien civilizations while living inside a cosmic intelligence that operates on scales we never thought to examine. The universe itself might be the alien intelligence we've been seeking." But Webb's revelations about cosmic intelligence pale in comparison to what the telescope discovered when it turned its attention to the nature of time itself. By analyzing how light propagates from the most distant galaxies, Webb has found evidence that time doesn't flow uniformly throughout the universe. Instead, it appears to move at different rates in different regions of space, creating temporal landscapes that challenge everything we thought we knew about causality and cosmic evolution. In some regions, Webb is observing galaxies that appear to be aging much faster than they should based on their distance and the amount of time light has taken to reach us. In other areas, galactic evolution seems frozen, with stellar populations that should have changed dramatically over billions of years, showing almost no signs of temporal progression. It's like discovering that the universe contains pockets where time moves in fast forward and others where it nearly stands still. The implications for our understanding of physical reality are staggering, because uniform time flow is one of the most fundamental assumptions underlying all of modern physics. The temporal anomalies also correlate with the cosmic information processing patterns in ways that suggest time itself might be actively managed by whatever intelligence is operating through the cosmic web. Regions where information flow is most intense show the greatest temporal acceleration, while areas with minimal cosmic communication seem to experience slower time flow. Dr. Sarah Kim from Harvard captured the scientific community's bewilderment when she said we might be living in a universe where time is not a fundamental dimension, but rather an emergent property of cosmic information processing. If that's true, then our entire understanding of cause and effect, of past and future, might need complete reconstruction. Meanwhile, Webb has been conducting what amounts to cosmic archaeology on an unprecedented scale, analyzing the chemical signatures of the most ancient objects it can detect. What the telescope found in these primordial remnants is rewriting our understanding of how complexity emerges from simplicity throughout cosmic history. The earliest galaxies Webb can observe contain chemical elements arranged in patterns that suggest molecular self-organization, operating on scales spanning entire galactic clusters. These aren't random distributions of atoms and molecules, but organized chemical networks that appear to be processing information and energy with remarkable efficiency. It's like discovering that the periodic table itself might be capable of computation, with different elements serving as components in vast chemical circuits that span millions of light years. The organizational principles governing these cosmic chemical networks show mathematical relationships that mirror the most sophisticated biological information processing systems. The discovery suggests that the boundary between living and non-living matter might be far more fluid than we've assumed. If chemical self-organization can operate at galactic scales, then the entire universe might be more alive than our terrestrial perspective has allowed us to recognize. The James Webb Space Telescope has torn apart everything we thought we knew about cosmic reality and replaced it with something so extraordinary that we're still struggling to comprehend what we've discovered. From impossible galaxies that shouldn't exist to evidence of cosmic intelligence operating on scales that dwarf human imagination, Webb has revealed a universe that's not just stranger than we expected, but potentially stranger than we're capable of understanding with our current scientific frameworks. The telescope continues its relentless survey of the deepest mysteries, and if these first few years are any indication, we're only beginning to scratch the surface of cosmic secrets that will reshape our understanding of existence itself for generations to come.